Let's get started. I hope everyone had a good lunch. Thank you for coming out here today to listen to my presentation. Today I'm going to be talking about a new category of wearable technology. Not just a new wearable device, but a whole new way of maybe looking at wearable devices. And instead of the sort of wrist-based devices we're so familiar with, this is an attempt to put all the wearable technology into the bottom of a shoe, into a shoe insole. For those of you grading me, I've laid out a nice roadmap that should make it easier to see which section I'm talking about. I intend to spend about 5 minutes on each section, and I'll come back to this in between various slides. Let's get started with some context on wearables, but specifically I want to focus on the concept of quantified self-tracking. Now, in a word, this is collecting your own health data for your own analysis. Think about Apple Watches, think about Fitbits, any sort of device that allows you to track data about your health just for your own review. I have screenshots from 3 apps here. One on the left here tracking sleep patterns. This is the number of steps taken over the course of a week, and then a smart scale that does weight. This has become really popular in the last 10 years or so as a sort of supplement to traditional healthcare methods. There's benefits beyond just the individual for quantified self-tracking. This is from a BP website. I actually pulled this just a week ago, where there's an incentive program. BP gave its employees free Fitbits and said, if you share our health data with you, we'll give you the ability to have a better health insurance plan if we can see that you're being active. You can see this as sort of a pre-primary care type of primary care, incentivizing healthier lifestyle, reducing healthcare costs for all of the parties involved. So there's clear benefits to quantified self-tracking, but one of the limitations of this quantified self-tracking is most devices rely on being on your wrist, your Apple Watch, your Fitbit, and there's 2 drawbacks to that. Primarily the aesthetic drawback. Some people don't like the look of these devices, and a level of comfort drawback. They're a little bit clunky and can run into things. My thinking is, why can't I create a device that eliminates these drawbacks and allows you to participate in quantified self-tracking without having to wear something on your wrist? And that's the quantified self-tracking insole, or the QST insole, which this project is about. Now, this is a high-level overview of the technical specifications, but it really comes down to 3 factors. I want to track the number of steps taken by the individual, the number of hours they spend standing, and the number of flights of stairs climbed, stories climbed in here. This is akin to what most health tracking devices on a wrist could do, but instead doing it from the bottom of an insole. There's actually precedent for putting sensors in shoes. This is from a 1994 patent from an inventor named Thomas Wood, might be related to Rob. This guy invented a smart shoe, and this patent actually claims a device to measure the number and force of steps that have been taken by the wearer. You can see that this is very similar to the work I'm doing, although there's other parts of this patent that diverge a little bit from my work. Mainly this inductively coupled data link. Essentially, you read further in the patent, and you can only use the device inside this little playpen that ensures all of the data gets transferred successfully to what's around it. This patent expired in 2011, and what I'm trying to do with this project is to extend this idea to an insole transferable between shoes. You see a few later patents, one in 2006 related to helping diabetic patients with selective warming and cooling of the insole, and there's one from 2014 related to a quote-unquote massage layer inside the insole, which is an interesting development as well. Here are some of the raw technical specifications for this product. This is what you might see on the back of a package or something for a consumer product. I want to highlight 2 aspects of this set of specifications, mainly the weight. The weight is chosen to be between 3.2 ounces and 4.8 ounces. This is approximately 1/10 the weight of a standard shoe, and the goal of this is to make it virtually unnoticeable for anybody who's wearing it. The thickness, the other important metric here, is chosen to be between 0.4 and 0.5 inches. I selected a sample of around 5 or 6 currently available consumer insoles, and the thickest thicknesses were kind of in that range. So I want to make it indistinguishable from what's currently available on the market. This next slide, these are more technical specifications, more related to the engineering, the sensors, how this thing is made. There's 2 primary categories of data I need to track, which are the steps taken, some sort of pressure force sensor, as well as the change in altitude, some sort of barometer, altimeter, or accelerometer. The altimeter should have plus or minus 2 meters relative to sea level. It's really the relative heights that matter, so the absolute height relative to sea level doesn't matter here, but plus or minus 2 meters resolution. One story of a building is around 3 to 4 meters, so this allows you to distinguish between stories. And then step counting accuracy, I want to have plus or minus 1% from the true step count. Really, this should be perfect accuracy because it's literally inside the shoe, but 1% with the size of data that I was working with is a reasonable accuracy to aspire to. Let's move on to some of the design aspects of the project. I've separated out the electrical and the mechanical design. I'm going to walk through all of the electrical, then all of the mechanical, and then we'll talk about the data. And the first step of this design was choosing sensors. For this device, as I mentioned, there need to be two types of sensors. There's the force/pressure sensors, and there's the altitude barometer sensors. Here I've chosen a force-sensitive resistor for calculating or getting the pressure data. I briefly tested two other materials, a velostat material and a load cell. In the report I talk about why those weren't chosen, but essentially the force-sensitive resistor has the best combination of accuracy and repeatability for the data. A barometer was also chosen. This is a BMP 388 from Bosch, and it was chosen over an accelerometer for the altitude data because it provided enough data without being too complex. The accelerometer faced the issue of being a little bit too much data for what I was trying to get. This is a block diagram for the first build, this Proto 1 build, purely electrical, meant to understand and validate the sensors. You'll see the force-sensitive resistors, as I talked about, as well as the pressure sensor. The calibration circuitry is essentially a set of voltage dividers, turning these variable resistances into analog voltage inputs. And then all of the data is read through an Arduino micro and then sent through the computer using the onboard micro USB port on the Arduino. This is just meant to be quick, a fast, easy way to collect data and then use that data to draw some conclusions. In order to have a base to put this on, I went out to Primark and bought the most ordinary basic pair of shoes I could find. This is in a size 10.5, which apart from being my shoe size, is conveniently the average shoe size in the United States for men. I took out the insole, this piece here, and basically taped on the pressure sensors in 4 locations. A heel sensor, this is the inside ball of the foot, outside ball of the foot, and the big toe. Secured it with tape, ran wires to the top, and they come out the side of the shoe. This is from the side of the shoe out to the top. Once those wires came out carrying that analog data, it's attached to what I call the processing block, which is placed on top of the shoe and secured with Velcro. That includes the Arduino micro and all of the other components of the circuit. This is obviously a very, very crude build, and the main purpose of this was to get data as quickly as possible. There are many shortcomings of this, the most obvious of which is that this is a moving assembly on a breadboard, which can lead to wires getting pulled out, things getting unplugged, just a lot of messiness with this sort of design. But the goal was to just produce data early on. Many of these shortcomings are addressed in the Proto 2 build, which is once I had some data and some understanding of what this circuit would look like, I decided to upgrade to a printed circuit board and a slightly more self-contained design, and that's Proto 2. This is a block diagram for Proto 2. You'll notice it's more or less the same as Proto 1. The biggest difference is instead of that Arduino micro, I've just switched to the pure microcontroller. This is an ATtiny44, much smaller form factor, and also can go on the PCB directly instead of being a separate board. And then I also have the micro SD card slot on there as well. The idea here was instead of having a wire coming out of the device, I could write the data directly to the device, make it more portable, make it easier to collect data as I was using it. Here's a schematic that I designed using Eagle. This would ultimately be transferred into a printed circuit board format. I want to highlight the biggest categories of the circuit here. The ATtiny44 is the microcontroller on which everything is built. The SD card holder is this section here. I have an FTDI header, which replaces the micro USB header in the Arduino micro. And the reason I chose an FTDI header is it has a much smaller form factor, only 6 pins, and it doesn't have the same Z height as the micro USB. The micro USB is a little bit bulky, so the FTDI allows it to fit into a smaller area. What is kind of interesting about this schematic is that I have 4 0-ohm resistors in this schematic, and those are actually for jumpers, for routing of the board. Here's the ultimate routing of the board. This is the one image that doesn't show up super well on this screen. I'm going to just flip over to the production of the board because it's a much better image of it. I chose to mill this PCB. So this isn't technically a PCB. This is a MCB, a milled circuit board, which meant this is a 1-layer board milled from a copper, kind of a substrate with copper deposited on it. It only has 1 layer. There's no way to add vias for this kind of production, and it has an incredibly restrictive design rule of minimum 16 mil clearance between the traces. Because the end mill used to clear out the in between the traces is 1/64 of an inch, or about 16 mil. What this meant was with a 1-layer board with such large traces, several jumpers were needed to route power lines and all of that throughout the board to make it all work. So this is cutting the board on an SRM 20 mil. and then cutting out the outline ultimately to this shape using a slightly bigger end mill. I like this because the production speed of this was a lot faster than a fab board. This took about an hour versus a fab board taking about a week. So it was good for getting quicker data for the Proto 2 unit. Of course, soldering the board, here's a picture of once all the components are added on there. You'll notice these are the 0 ohm jumpers I talked about before. Soldering for this board was relatively straightforward. All the resistors and capacitors on this board were chosen to be 1206 components, which are a little bit bigger. I tend to use 0603s on smaller boards when size matters, but for this board, since it's one layer, there were oftentimes I had to route traces underneath the resistors. So having a 1206 allowed 2 traces to pass underneath, allowing a lot of this routing to work. There's a lot of complexities in this board, but in the interest of time, I'll move on. This is the completion of the electronic part of the design. I have the board, I think I showed it to a few of you briefly, but let me grab it real quick. I have the finished circuit board here. But as a standalone piece, the circuit board isn't that useful. What it really needs is a mechanical housing to fit into the greater design. Now I should say at this point, I'm an electrical engineer, but I love mechanical engineering, so the next few slides are something I enjoyed doing, kind of supplemental to the project, not directly related to the electrical part of it. I had to build an insole to support this board. And the idea behind this insole was, how can I separate this out in a way that makes each layer distinct and serve a purpose toward the greater insole. This is the Z stack up of my 3 layers of this insole. And I think you can see the total height of this thing adds up to 0.43 inches. I'll go into why each layer exists and what it does. This is generally what I aimed for. I wanted the 3, 4 sensors near the front of the foot, the 1 large one on the heel, and then the motherboard sitting in the kind of arch of the foot where there's a lower pressure. The first layer, I called the base layer, I also called the sensor layer, is this right here. You see wells here that hold the pressure sensors, 3 in the front, 1 in the back, and these wells sort of route wires to the side of the board where they can then go up to the second layer. This is the produced version. This will be more relevant a little bit later when I get on to how these were produced, but this is the first layer, the sensor layer, the base layer. The second layer is what I call the motherboard layer, or the MOBO layer. This is the thickest layer of the insole, and there's the most noticeable part of this is this deep well in the middle. That deep well is where the motherboard goes, and so I can take that and just drop it in there, and it's sort of secured into that spot by the layers below and above it. You'll also see a little cutout here for popping the micro SD card out, a little cutout here for attaching an FTDI cable to stream data out if the micro SD has problems, and a little well down here into the sensor layer for the wires to come up and through. And lastly, the top layer, which is mainly for aesthetics and mainly for containing the rest of the layers inside. This is actually made from a different material. This is a flexible resin, whereas the other 2 were made from the tough resin, but this is purely aesthetic. All of the layers stacked together, we get a Z height of 0.43 inches with all of the devices contained in there, including the height of the electronics on the circuit board. So this was a very involved systems design project that involved understanding the height of components on the circuit board when it came to designing the layers. I produced this on a Form 2 printer. This is a stereolithography printer. You'll see on the left, this is in the software preform, setting up the various components. The print bed of this is only about 6 inches by 6 inches, whereas this insole goes up to about 9 inches. So I had to break it up with tabs to allow it to print on that printer. And you'll see it nicely lined up. This picture is from the printed product. It's the same model and perspective as here, but this is after being printed. And again, here are the 3 layers once they're done printed, also sitting right up here at the front. That's all the production. At this point, I want to get into a little bit of the data. And I want to put a disclaimer here that all of this data you'll be seeing is from the Proto 1 unit. The Proto 2 unit, it would take a while to explain the difficulties with it, but essentially there were some problems with the mechanical design that allowed the PCB to kind of get squished. I overestimated the strength of some materials, but for now, this is all good data from the Proto 1 unit that could be used to inform building the Proto 2 unit and future designs. There's a lot of data that came out of this project. These are all of the samples that will be showing up in my report. They fall into the 3 categories of the steps taken data, standing hours data, and the flights of stairs data, but what I really want to focus on in the interest of time for this presentation is the steps data, with a little bit of barometer data at the end. the steps data actually informs the standing data and the flights of stairs data. It's the data from which all the other things can be derived. So I want to look at some data related to steps. Here are 6 graphs of 6 different samples of 10 steps taken with a right foot with the Proto-1 unit. And these are a little bit hard to see, but I just wanted to show the breadth of the data in this slide. I'm going to go a little more into what it looks like at a granular level and the sort of processing I did to it. But here's just a collection of some of the data. Here's the third of the 20 samples. I picked this one because it's got some nice features that'll be representative of what the processing I'm going to do to it is going to do. You'll see that the 4 pressure sensors here are notated by lines corresponding to what they're marked on this foot here. The yellow line, the heel, seems to lead the other 3, the inside ball, the outside ball, and the toe, and they tend to have a pretty good rhythm related to the frequency of steps. I want to point out 2 things here, which is the outside ball has this really high frequency noise in a few spots, which is kind of annoying for when you're doing thresholding to try to count steps. This high frequency noise can really mess up that count, so that's something that needs to be addressed. Also, I sort of mentioned before, the heel sensor always seems to lead the front of the foot in most of these data samples, and that seems to make sense as people step with the back of their foot before the front comes down. I want to talk about processing this data now. And the first step is obviously to remove some of this high frequency noise. I chose a pretty simple filter. This is a simple moving average. It takes whatever your current value of pressure is, averages that with the previous 10 values, and uses that to determine what the value is at that point. This can also be thought of as a low pass filter, removing a lot of that high frequency noise. So you'll see these spikes in the outside ball data become very, very smoothed out by application of this filter. This essentially allows thresholding to be a lot easier and for the high frequency noise to be rejected, only taking the larger components of the step data. Another thing I noticed is that the front of the foot, you'll see that the 3 data points for the front of the foot, these are all roughly in sync. The amplitude is a little bit different, but in terms of phase, they're all similar, whereas the heel sort of leads them in all cases. So I thought, from a data processing perspective, it would be a lot easier to consider the front of the foot all as its own set of data. So that's what this graph does. It aggregates, just takes an average of the front 3 sensors, the inside ball, outside ball, and the toe, and then again running that filter on it. So now I have a much cleaner data set that just involves the back of the foot and the front of the foot. From here, it just became a matter of setting thresholds and counting steps. So this next graph takes this is the unsmoothed data, the smoothed data, and then binary data. This is essentially a comparator operation where the threshold is asymmetric across the center point. So the values go from 0 to 1,000 on the ADC. The threshold for changing from a low to a high is set at the 80% value, so it's set at 800. So anytime it goes above 800, it converts over to high, and then once it's high, the new threshold is set at 200. So anytime it drops below 200, it drops to a low. So this allows for this nice binary encoding of the data and rejecting sort of the noise in the middle that comes from something like standing. Not included in this presentation, but relevant. The standing data is essentially a much longer time scope version of the same algorithm. I ran this algorithm. So the step counting algorithm that derives from this is a simple next step, which is anytime the value changes from 0 on the front, 0 on the back, to 1 on either of them, there's an OR operation here, that logs a step. That means you can step with the back of your foot or the front of your foot and it'll count as a step. And it doesn't reset or clear the step until you get a 0, 0 measurement. I ran this on all 20 samples and counted the true number of steps. So you'll see most of these have 10, a few of them have 12, 11, just to test other values. The step counting algorithm reported the correct value in all of these cases, which is a testament to how robust it seems to be. There's actually a few interesting edge cases here, and I want to highlight these. This is from sample 12 and sample 19. Sample 12 has what I call an indecisive step. This is where the heel made contact and then the front took a while to make contact as well. This is actually from skipping, interestingly, or this is a byproduct of a step that resembled a skip. And what's nice is since I use the front or the back to indicate the step, the fact that this is completely separated, the front is separated from the heel, doesn't affect this. This is still counted as one step without any problems. There's also sample 19. This is from going upstairs. If you can think about your motion as you're going upstairs, the front of your foot usually leads the heel. And the heel measurements here are really low because the stair was relatively narrow. In this case, the steps are still counted correctly, even though there's no heel measurement. So by measuring at the front and the back, I'm able to account for instances like this where only one of them is tracked. Of course, to test the robustness of this data, I tried it on a much larger data set. This is 100 steps. And I actually have 5 data sets that have this 100 steps to see if I could count all of those steps successfully. And the results were perfect. From these 100 steps, there were no failures in categorizing the data. So this step counting algorithm works pretty well. You can see a section here where I'm going upstairs, so the heel is not making contact. Classified that without a problem. Let me talk very briefly about the barometer now. The barometer data is essentially returns a value relative to what it thinks absolute sea level is. And so here are some values at various relative heights. So I started at 0 meters, moved it up 2 meters, took a measurement, or took 100 samples and averaged it, and then so forth. These data do correlate to changes in altitude just by a scale factor. So the gray line, so anchoring all to this relative point of 0, the gray line shows where the reading should have been if it was completely accurate to the spec within the data sheet and all of that. In reality, it is slightly lower, but this is just by a scale factor. So it looks like the barometer is effectively able to tell the difference between something like 3 meters and something like 0 meters relative. There is a little bit of error in here. You can see that the error bars, which are included on this graph, have a little bit of range to them, but in general, if you look at the numbers, this is enough to distinguish being 1 story up from 1 story down. That's everything for data. I just want to highlight, since this is a senior capstone project, I think it should represent the work I've done during my time at Harvard. These are all of the technologies that went into producing this. Principally of them, I had Eagle for designing the PCB and a lot of data processing using Python, but this is just a selection of the technologies that were used. In the future, I would like to really make some improvements to the mechanical design of the insole. There's a lot of wasted space near the front of the insole, and this was more a matter of you choosing a simple design rather than a perfectly efficient design. There's opportunity for some material saving and some weight saving in that regard. Also putting a battery in there. This is something I cut from the design because of safety concerns, but ultimately I'd be curious if there would be a way to integrate a battery into the device itself. I want to say a big thank you to all of the folks that helped me along in this project. I think the biggest thank you definitely goes to Mike for listening to me talk about these circuits time and time again, walking me through design decisions and helping bring this project to fruition. I want to say a huge thank you for everyone coming to listen to my presentation. I look forward to hearing you guys' questions. Thank you very much.